Welcome to This Explainer. Today, we're diving straight into a truly mind-bending mystery, the atmospheric collapse of Mars. You know, when we look up at the night sky, Mars just looks like this quiet, static red dot, right? Well, it turns out, beneath that calm exterior hides a climate history that is incredibly dynamic and, honestly, pretty violent. We're going to unpack some groundbreaking simulation data that shows how the red planet's entire atmosphere can literally freeze and fall right out of the sky. Let's get into it.
So what actually happens when a planet's entire atmosphere just freezes to the ground? It sounds crazy, right? Imagine just standing outside and the very air you're breathing suddenly turns into snow and buries the landscape. I mean, it sounds like pure science fiction, but this is a very real fundamental physical process. It's a process that completely shaped our neighboring planet and basically dictated whether Mars ever really had a shot at sustaining a warm, wet environment.
To wrap our heads around this, we really need to nail down what scientists mean by atmospheric collapse. Basically, it's what happens when a planet's atmosphere completely deposits its carbon dioxide straight onto the surface. This leads to the massive, multi-year growth of at least one permanent CO2 ice cap. When a planet hits this deep freeze, the atmosphere practically vanishes into the dirt. And why does that matter? Well, it fundamentally limits the time a planet has for any physical or chemical weathering. Any rivers, any lakes, they'd freeze solid in an instant. The geologic clock essentially just stops.
Part 1. The 3 Martian climates. See, the Martian atmosphere isn't just one static thing. It actually has 3 totally distinct climate states. Depending on the conditions, Mars acts like 3 completely different planets. It can be a world completely free of surface CO2 ice, a transitional world undergoing a rapid, aggressive freeze, or a fully collapsed world where the atmosphere is locked in a frozen thermodynamic balance with the surface. The math behind this is brilliant. When looking at the relationship between surface pressure and temperature, there's a delicate balance. Down at what scientists call point A, we have a stable, collapsed climate and vapor balance. Up high above point B, we've got a thick, stable, non-collapsed atmosphere. But look right at point B itself. That is an unstable tipping point. If the planet's temperature or pressure drops even a tiny bit below point B, boom, runaway cooling. The atmosphere starts rapidly freezing out, sliding all the way down until it hits rock bottom at point A.
Moving on to Part 2, Flaws in Past Models.
For the longest time, scientists actually thought they had this transition point totally figured out. But, spoiler alert, the older modeling tools severely underestimated what was really going on. Researchers were basically trying to predict ancient Martian climates while wearing a meteorological blindfold. These older energy balance models treated the atmosphere like a flat, one-dimensional gray blanket. They just calculated energy in, energy out with super simplified wind. But modern general circulation models, they use full, three-dimensional dynamic weather simulations. They finally treat Mars like a real, rotating sphere with mountains, valleys, swirling winds, and super complex chemistry.
So, what was the big issue? Well, using just a single constant number for heat transport in those old models was a massive weak link when trying to simulate a climate right on the edge of total collapse. Those old models assumed the atmosphere absorbed radiation evenly across the board. They completely missed something called collision-induced absorption. That's what happens in a thick CO2 atmosphere, when molecules are physically crashing into each other, trapping heat in a completely different way. And by ignoring the actual 3D flow of wind, the transport of air from the equator up to the poles, they totally missed the actual mechanics of how Mars freezes.
Which brings us to Part 3. Enter the 3D simulator.
To actually solve this puzzle and figure out what really happens on the red planet, researchers brought out the big guns. They needed to stop guessing about the wind and actually simulate the weather. Enter Mars WRF. This is an incredibly powerful 3D general circulation model that brings actual realistic physics into the mix. Instead of just flat math, Mars WRF explicitly solves complex transport equations. It maps out the actual topography of the planet and tests out different amounts of total CO2 against various planetary wobbles. It basically lets scientists hit play on Mars and watch where the snow actually falls.
And when you graph the sheer volume of global CO2 ice building up over time, a crazy pattern emerges. Even when testing completely different starting thicknesses for the Martian atmosphere, the data almost always trends aggressively upward. This proved, without a doubt, that those earlier 1D models were just dead wrong. The real 3D physics revealed that Mars is way more prone to atmospheric freezing than anyone originally thought. It turns out, atmospheric heat transport is often vastly insufficient to stop that deep freeze.
Part 4. The wobble controls everything.
Okay, so the total amount of carbon dioxide gas a planet starts with, that's only half the story.
The planet's axial tilt, its obliquity, is basically the master switch for its climate destiny. The angle Mars tilts toward the Sun dictates literally everything. A low obliquity, so anything from 0 to 15 degrees, guarantees a total atmospheric collapse. Period. It doesn't even matter how thick the atmosphere starts out, the poles just stay way too dark and way too cold. It isn't until the planet reaches a really high wobble of around 45 degrees that the poles finally catch enough direct summer sunlight to stave off the freeze and keep that CO2 up in the air where it belongs.
And this is a crucial detail because the Martian obliquity cycle naturally oscillates over a massive 120,000-year period. Over eons, Mars is just slowly nodding back and forth toward the Sun. That means the planetary trigger for a total atmospheric freeze is naturally pulled on this massive, slow geological clock. But here is the wild part. Compared to that massive 120,000-year cycle, the actual event of a complete atmospheric collapse happens ridiculously fast. For a thin 6 millibar atmosphere, once it hits that tipping point, the entire atmosphere can collapse into ice in just 100 years. 100 years. In cosmic terms, that's not even a blink of an eye. An entire planet can go from having a viable, swirling atmosphere to a dead, frozen vacuum in the span of a single human lifetime. Mind-blowing, right?
Part 5. Olympus Mons steals heat.
Right in the middle of this rapid freezing, the 3D simulations uncovered a completely unexpected villain hiding in plain sight. Something massive was disrupting the whole global climate, and the old flat models obviously never saw it coming. Olympus Mons, the largest volcano in the entire solar system. It acts like this greedy cosmic vacuum cleaner that literally steals heat that was meant for the poles. Because this mountain is just so huge, it increases the local atmospheric pressure right at its location. Higher pressure means CO2 can condense into ice at warmer temperatures, so it literally starts snowing dry ice directly onto the volcano slopes. This local freezing creates a massive pressure vacuum, a condensation flow, that actively sucks in the surrounding atmospheric energy. This localized heat theft completely rewrites the global math, because Olympus Mons is intercepting and hoarding all this heat that the wind was desperately trying to carry to the freezing poles. The poles get totally starved of warmth. This absolutely accelerates the collapse across the whole planet. It's the perfect example of why those early 1D models were so fundamentally wrong. You simply cannot understand Mars without understanding its crazy topography.
Part 6. The Collapsed Reality.
So, what does the planet actually look like when the math finally settles, the volcano has stolen all the heat, and the atmosphere hits rock bottom? Well, researchers ran what they call an inflation simulation. They started with almost all the CO2 already frozen on the ground just to see where things would stabilize. And what they found is that whether the atmosphere is collapsing from a thick gas or inflating from solid ice, it always finds a steady, stable vapor pressure balance. In this specific scenario, it stabilizes at roughly 25 millibars. At that point, massive, permanent CO2 ice sheets rule the poles, and the super thin air just cycles seasonally right above them. Tracking this collapse over a timeline shows exactly how aggressively and systematically the climate locks itself into a frozen reality. At year 0, the tipping point is crossed, and rapid deposition begins. Within just half a year, 6 months, the surface energy balance totally equilibrates. By year 2, the planet establishes a new, desperate seasonal cycle as the atmosphere effectively dies. And by year 100, the thin atmosphere has completely surrendered, locking the entire planet into a state of permanent surface ice. Knowing how easily Mars slips into these rapid, deeply frozen periods, and how a slight orbital wobble can literally turn the air into ice within a single century, well, it severely limits the windows for any warm, wet conditions. Which leaves us with one incredibly provocative question. Considering this violent, freezing pendulum, did the red planet ever really have enough uninterrupted time for life to take hold? Definitely something to think about the next time you look up at that little red dot in the night sky. Thanks for joining me on this explainer, and as always, keep your curiosity alive.